I'm going to talk about mainly amorphous oxides and what we discover about electron trapping and polarons in there. But I will start from also talking about polarons and crystals and some comments which we can make about functional. So this is a different type of talk. So we are talking about DFT. So a lot of people have been involved in this over the years. Most of them are mentioned here, and we collaborated also with Stefan and Alex Zunger at some point, and also some experimental guy, Katsumi Tanimura, and Valeria Afanasyev. So yeah, this is a fantastic meeting, so thank you very much for inviting me to participate. I mean, the main question for me, after many years of dealing with these polarons is, can we accurately predict the existence of polarons and their properties? So we have been calculating polarons and their properties for many years, but prediction is still quite elusive. So since it's 21st century, I will start from some of the papers which were published at the beginning, which have been mentioned. So at that time, at around 2000, people made cluster calculations using different functionals for well-known Hole center, aluminum center in quartz. So there were two papers by Gianfranco and his group, and also by Kurt Stockbrough, which basically concluded that, say, if you use GGA, you cannot localize a hole, and so you need to have some better description of exchange, to deal with that. So we also were involved in this kind of story, and so we looked at now in periodic model, and so this is a big difference, because we were very excited by the fact that at that time, say, crystal code was working, and WASP also was starting to work, and so one could actually try to look at localization. In this case, it is exciton. What we're talking about is exciton in sodium chloride, and so this is the way how it gets, say, decomposing into defects. So this is formation of F center and interstitial oxygen. How this can be represented in GGA, and turned out to be a complete failure, and so we also made the conclusion that, say, attempts to use GGA for localization are not working. So at the beginning of this century, self-interaction error has been recognized as preventing correct localization in DFT, and the absence of electron correlation in unrestricted Hartree fog, which has been used before that and was always over-localizing the polarons, I mean, for previous 20 years. So led to the compromise that basically, okay, so let's try to use hybrid functionals. And some of them have been implemented at the time in the codes like Crystal. And so, therefore, it became possible. So the question again is, can hybrid functionals correctly predict polaron self-trapping? So at the same time, very convenient materials came out into production. And so in microelectronic industry, these two materials became very useful, so hafnia and zirconia. So say hafnia has a monoclinic phase as its stable phase, which has 4 and 3 coordinated oxygens, and it has very high dielectric or relatively high dielectric constant to previous materials like magnesium oxide or alkali halides like 25. So therefore, one could expect that maybe some polaron trapping could happen in these materials. And indeed, so we try to make a prediction of that, which has been already mentioned. So at that time, we used Crystal, which was the only code which was implementing B3LIP as a non-local functional. And we predicted that, say, in this material, you can trap both electron and hole polarons. So both of them can be localized. And so self-trapping energies, the difference between delocalized and localized energy states were positive, and they were of this type. So what we were talking about 0.3 electron volts for, say, electron trap, electron polaron, and say 5 volts for free coordinated localization of hole on free coordinated oxygen. Okay, so that was a prediction. Experimentally, I will talk about that later. It was very difficult to prove, but later, as Stefan already alluded, people paid attention to the fact that actually these functionals and the behavior of these functionals is actually not complying with Koopman's condition. And so this was published, say, around 10 years ago. And Stefan already talked about this. So we use this technique together with Stefan and Alex Unger to look at the same polarons. So in this case, we fitted this parameter lambda in order to represent one center Hole localization in monoclinic Hafnia and looked at how this may happen. So this functional was a GGA functional, but it was eliminating self-interaction using cancellation of nonlinearity method, which Stefan talked about. So as a result of that, we have, again, Hole trapping, which we were thinking may be better described in this type of, using this type of functional. And what turns out is that actually, say, holes trap only on free coordinated sites, say, shown here, although in both cases we have localization. But if you look at potential energy landscapes, only free coordinated sites actually give you trapping energy, which is positive, and four coordinated sites actually are metastable. In both cases, actually, there is a barrier for trapping. This barrier is quite elusive, so has not been discussed yet at this meeting, but in this case, we were able to calculate this barrier. So there is a small barrier for self-trapping in this case, and prediction was in this paper that actually only, say, Hole localization on free coordinated sites is possible. Now, if we compare free functionals, in this case, B-free leap, so it's our old prediction, then cancellation of nonlinearity, and then at that time, HSC became prominent. And so we tried also HSC and compare, say, self-trapping energies. So you can see that, say, we get quite different numbers, in particular between B-free leap and HSC. So CON and HSC, interestingly, predict very similar qualitatively kind of behaviors, that actually holes will be localized only on free coordinated sites, and on four coordinated sites there is negative value for trapping energy in a stable state, which is still can be localized, but I don't think will can be observed. Interestingly, is that say the difference in trapping energies between free and four coordinated sites proved to be quite similar, as well as position of one electron hole level. So this actually brought further questions. Okay, so how to deal with prediction? Because now we have free functionals, and we have qualitatively different answers. So in some cases, we predict that the, say, hole may be trapped. In some cases, they cannot be trapped. So what to do with that? So
just a short question. So the structure is the same for the three functionals here, or each structure has been optimized?
So each structure has been optimized with each functional, and so everything has, geometry has been optimized in periodic boundary conditions, in that case in the same cell. So we returned to this question recently, say, trying to see whether, say, we can say anything about this localization using different functionals, paying attention to the fact that actually what we are dealing with is trapping energy, and so trapping energy is the difference between the localized and localized state. And so therefore, potentially, it may be that, say, short-range and long-range exchange may be playing some role in these calculations. And so maybe one needs to pay attention to that. So we teamed up with a group of Leo Kronig at Weizmann Institute. So this is David Wing, who did most of this work. And so we came back to these defects. So these are V centers and lithium zero centers in magnesium oxide. The reason for that is because they have been studied experimentally quite well. And so if you look through the literature, you can kind of justify trapping energies for these, say, two defects, unlike anything else you can find. I mean, there are no experimentally justified trapping energies for any other polarons. So we started to look at this lithium zero center and this V minus center, which are well-known Hole centers, trying to see whether we will see any difference between behavior of free functionals. So one functional which we are using quite a lot is PB0 truncated Coulomb and long-range corrected functional, which is implemented in CP2K. So CP2K we use because it is quite efficient, but efficiency comes exactly from this functional because it is truncated. So the exact exchange is truncated here up to some radius. So this is determined by this expression here. And then beyond this radius, it is represented at PB as a spherically averaged PB exchange hole. And so what we were trying to achieve with these functionals is the same thing. So we were asking a question, okay, so can we actually satisfy Kuhlmann's compliance and band gap at the same time? Because this would be useful for these calculations, and get, say, the same trapping energies. So this is PB truncated. Then we used also HSC. So for this functional, we found that actually we can satisfy Kuhlmann's compliance with 32% of exchange at, say, truncating the functional or exchange in this functional at 6 angstrom. On the other hand, in HSC, exchange actually is dying in this way. And so then, so if you use normal HSC functional, HSC06, you get wrong band gap, about 6.4 eV. So if you increase the amount of exchange, you get, say, to this value, you get the experimental value of the band gap. And in both cases, you can achieve some Kuhlmann's compliance, but in this case, actually, say the error is quite large. So the best compliance is actually when you don't get the band gap right, but say you can still satisfy Kuhlmann's. And then there is the range-separated hybrid. So range-separated hybrid behaves completely differently in terms of exchange. So it has some short-range exchange, which is lower, say, close to the atom, and then it is increasing. And so there are two parameters, alpha and beta. So this alpha and beta satisfy this relation. And this functional basically is supposed to have correct asymptotic behavior with increasing distance, with screening at epsilon infinity. So this has been developed by Leor Kronig for a while, and so it has been shown for molecules actually behave pretty well. And so we were thinking, okay, so maybe we can apply it to solids and see what will happen. So in all three cases, what we did, we calculated band gap and Kuhlmann's compliance using this expression and tried to satisfy both. And so the result is here. So what you see is, say, if you use just a normal HSC in WASP, so you predict, say, trapping energy for lithium-0 center of about 0.3 volts. Experimental value is 0.7. Range-separated hybrid is given about 0.9. If you feed HSC to reproduce a band gap, you overshoot and you get 1.1. And so with PB0 truncated, you get 1.2. So again, so what we are seeing is that, say, if we do for the V- center, which is a hole localized near cation vacancy, so we see, say, similar stories. So from experiment, we know that trapping energies are in this range. So HSC 06 give 0.9, range-separated hybrid is more or less in agreement with experiment. Fitted HSC is overshooting as well as PB0. So that means that actually, basically, from here, from this limited data on these several Hole centers, we can conclude that actually, on one hand, tuning a hybrid functional in order to satisfy Kuhlmann's compliance and band gap is, in many cases, impossible. So you cannot satisfy both. So usually, so if you want to deal with polarons, you need to go for Kuhlmann's compliance. And then it's important that functional has both long-range and short-range exchange in it, because range-separated hybrids seem to be behaving better than other functionals. So this is just to throw in for people to discuss, because this clearly shows that it's not only about the value of exchange, but it is about how exchange is implemented, what kind of exchange you are using, etc. In these functionals, what may determine, say, the outcome, if you are concerned about prediction. Now, I'm going to talk about further, say, what we did about electron-hole trapping in amorphous oxides. So we use the same oxides as I was mentioning before, say, Hafnia, and much more of these. I'm going mainly to talk about silica and hafnia in my talk, but there are much more oxides which we looked upon. Because many of them are produced as amorphous films, and so people were interested to see, say, the degradation of these films, and so this degradation happens under electron injection or hole injection in devices, and so therefore the question about localization is important. So this is methodology which we use. We need to produce amorphous structure first. So what we do is that we start from a crystal, we basically use melt and quench procedure, and in most cases interatomic potential. So we use some force field, use some molecular dynamics, melt our sample, and then say slowly decrease the temperature and quench it. So slowly, in this case, is quite fast by experimental measure. So we go down to about 1 Kelvin per picosecond. So experiments barely can reach that, so we are much slower. And then we fully optimize the geometry of this frozen melt or amorphous phase using DFT. And then after that, we inject electrons or holes into these systems and look at what happens with these electrons and holes, and so whether they get localized, etc. So for these systems, it's important to have statistics. So therefore, we usually calculate quite a lot of models. So it's, say, for silica, it's more than 300 models we construct, but of relatively small size because we want to do DFT. We use ReXFF for silicon dioxide, and we have another force field for hafnia. And so this is this melt and quench procedure, which I mentioned. And then in all of these calculations, we use CP2K as a code. This functional, as I mentioned before, PB0 truncated coulomb, which we do basically amend, or we fit it in order to get the band gap and the Coupland's compliance in a crystal of silicon dioxide and also hafnia, monoclinic hafnia, and then use it to predict what is going on in amorphous phase. And we use this auxiliary density matrix method, which Van der Wandel developed in order to speed up these calculations. So because we use so many models, so we really need quite a lot of speed because we need to turn the numbers quite quickly. So what you get in these calculations is that, okay, so if, say, for example, you take silica, inject electron or inject a hole, you can see that actually they don't get delocalized, sorry. So they get localized partially in your fully optimized amorphous phase. In this case, silicon dioxide is a glass, so therefore it is a continuum random network kind of a model of the glass. And so the density of states is shown here. So the band gap of silicon dioxide doesn't change very much on amorphization, but you have states which are present already in amorphous phase which pre-localize your electrons or holes. So we analyze the character of this localization using this inverse participation ratio method, which has been developed for amorphous structures for a while. And so it's particularly helpful for codes like CP2K because it is using localized basis set, so therefore it uses coefficients in linear combination of atomic orbitals to see how strongly states are localized. And so if you look at, say, these graphs, you can clearly see that, say, okay, so the highest value here corresponds to the degree of localization. So delocalized states have very small values, so these values are localized. And so you can see that in this case, it's amorphous hafnia. And you can see that at the top of the valence band and also at the bottom of the conduction band, you have some localized states which look like that. And then you have also delocalized states. So I'll come back to this, but there is a fundamental notion of mobility edge, which one needs to deal with in these materials because, say, these states here are localized, but then there is a band of delocalized states and mobility edge and etc. And so if we use this IPR analysis, then we can say, okay, so here are some states in the amorphous phase which get, say, this electron or hole localized initially. Then we can put extra electron into the system, optimize the geometry, and see how they will localize as a result of relaxation or polarization of the system, which say we would also be looking at in a crystal. But in this case, we have precursors. So the notion of precursor is very important in this situation, because we do have some structural features which actually pre-localize these states, as we can see from here, due to various, say, properties. And so usually this is low coordination. So I'm very pleased that Elio Gemello is here, because we worked a lot also on low coordinated sites on powders, like magnesium oxide and other systems. And there is a direct analogy between these states which we see on surfaces, for example, of magnesium oxide, which also localize electrons and holes, and these polarons which we see inside these materials, which are also trapped at low coordinated sites. So now, if we analyze the structure of these two materials, like amorphous silica and amorphous hafnia, so they're very different. So silica is a glass former, and so basically the structure of amorphous silica is well described as a continuum random network, where you don't change the coordination of silicon and oxygen. So silicon and oxygen are still coordinated in the same way in quartz, but you just have disorder of tetrahedra. And so you have this distribution of angles and distribution of distances, which is obviously a characteristic feature of these systems. Now, amorphous hafnia is not a glass former, so it is forming amorphous films. But in this case, the difference is that as a result of that, as a result of disorder, you have different coordination. So you have different coordination of hafnium and oxygen, so you have 2 and 3 and 4 coordinated oxygen sites, and they distributed in the lattice with some probability. So you have that, say, we use different sizes of the cells, as you can see here. Say 324 is our kind of working cell, and then there are bigger cells we looked at. So statistics doesn't change of distribution of these sites. So it's about 84% free coordinated sites, but then there are 6% of 2 coordinated sites. And so these sites, these 2 coordinated sites of oxygen and under-coordinated hafnium, are those which are responsible for trapping, and the concentration is quite different. So in amorphous phase, say electron trapping, for example, happens in open angle sites, sites which have oxygen silicon angle bigger than kind of average value, so at around 130 degrees. On the other hand, here it is mainly coordination of the sites which is producing potential well for trapping. And now if we put electron or hole inside, so electron in this case, and optimize the geometry, so we see that at these precursor sites, there is some very strong relaxation, which leads to full localization of electron, in this case on 1 silicon, and in this case on 2 hafnium ions. So it's very strong localization. So these are, you can call these polarons. We tend to talk about trapped electrons, because these are not fully polaronic states, but they are trapped at precursor sites. So now if you do statistics and you calculate this many times in different amorphous structures, etc., you have a distribution of these levels. So this distribution is very wide. And also you see that trapping energies, which we are talking about here, say average trapping energies, are much bigger than what I mentioned before. So for hafnia, for example, we were talking about say 0.3 volts for electrons, so now it is much more than, say, 1 volt, and so these states are much deeper in amorphous phase than in crystalline phase. So now, in the first day, we were discussing about how, say, what about experimental evidence? So it's quite difficult to prove. So silicon dioxide is the best material, so it is, say, glass, silicon dioxide glass is well studied, and so now let's see what one can do about this. So in glass silica, so if you inject electrons, say if you radiate the system at 80 Kelvin, you produce electrons and holes. So yeah, interaction, say irradiation of this material at the temperature produce electrons and holes, and both of them are localized. So that is a very important feature. And so people, there is an experimental paper by Katsumi Tanimura which shows that optical absorption of the system after radiation looks like this, at 80 Kelvin. So now, if you heat up the system to 180 Kelvin, both of these become mobile, they recombine, and as a result of that, the spectrum, optical absorption spectrum changes. So the differential optical absorption spectrum looks like this. There is a PR signal for this defect here, which is attributed to self-trap hole. So self-trap hole in amorphous silica has been studied by Griscom for many years, And so this is quite good attribution. So this is a Hole set. So it has optical absorption of about 2 electron volts. So this band here at about 3.7 volts, nobody knows what it is. And so therefore, we were trying to understand whether it can be attributed to self-trapped electron. So in this type of experiment, it is important to do kinetics. So as you irradiate, you can see that both say, types of absorption at 2 volts and 3.7 volts, they grow simultaneously, meaning that both defects are produced as a pair. And then if you anneal this, which is another part of this type of experiments, which is very important, they also die simultaneously at this temperature here. So it's about 180 Kelvin, which is a very characteristic temperature for these systems when holes become mobile. So holes become mobile, so they recombine with electrons, and both of them die. So therefore, I mean, the argument in this paper is that actually both species can be produced simultaneously. So what we try to do is to calculate optical absorption of the trapped electrons. I must mention the method which we use here because it hasn't been mentioned so far. It is embedded cluster method, which has been used very successfully for studying polarons generally in oxides and other materials for many years. Now it is not that popular because of periodic boundary conditions, but we still use it, so it is a natural code for polarons. So it allows you to calculate, say, relaxation of the whole system till infinity, and so it includes the quantum part, which is treated, say, in this case, using Gaussian code and be freely functional. Then it is surrounded by, say, quite a lot of atoms, like 1,000 atoms, which are responding to polarization introduced by the polaron inside, and then it has infinite lattice or infinite continuum of dielectric around it. So this is famous Mott-Littleton model, which has been introduced, I think, about 80 years now. And so using this model, we have calculated both self-trapped holes. So this was published in 2007. So this was the first paper on self-trapped holes in amorphous silica, which have shown that actually optical absorption of self-trapped holes is at around 2 electron volts. And then we also calculated recently the self-trapped electron in this model and calculated what is optical absorption spectrum of this electron using time-dependent DFT in this embedded cluster method. And what you can see is that basically the optical absorption band at about 3.7, 3.9 electron volt, which say is seen experimentally and has not been attributed, can be attributed to self-trapped electron according to these calculations. So there is quite a lot of statistic here, which is giving also inhomogeneous broadening to this band observed for this electron. So this is as far as we can go in terms of proving that actually these states exist. An important part of that story is that, say, if you add another electron to the system, so you form a bipolaron. So this bipolaron is deeper state, and so it is more, I mean, it induces more relaxation into the lattice. So this bond, for example, gets elongated to about 1.8 angstrom. And I don't have time in this talk, but basically this has huge consequences because we have shown that this oxygen then can move away with quite small barrier, and so you produce Frankel defects, and so this can produce some degradation in these oxides, etc. So now, in terms of Hafnia, there is the same question. I mean, we have shown that actually electrons can be trapped in Hafnia. Also, bipolarons can be produced. So in the same site, you can trap the second electron. This is producing a bigger relaxation. It involves some bigger displacements, as you can see here. So hafnium ions are moving closer to these electrons, and the oxygens are moving away. And what is experimental evidence? Okay, so Valery Afanasyev and his group in Leuven, so they looked at these Hafnia films in devices, and so they use a method which is called internal photoemission in order to study charging of these films. So you can charge these films by applying light and bias, so you can put some electrons in, and so you can see that these films get negatively charged, and then you can discharge them optically by exciting these sites one by one with some small increment and getting electrons into the conduction band. And so this spectrum of this excitation is measured, so it is shown here. So this is the spectrum of sites which are produced in the band gap as a result of negative charging of the system. So this, you see that there are sites at around 2 volts up to 3.5 volts in depth. So these are these maxima. So here they correspond to these electron traps. So this brings a quite fundamental question about how to deal with these disordered systems. And so what is actually measured? So here is a band of trapped electrons, both single electrons and bipolarons, which we have seen here. And so we calculate it again using time-dependent DFT excitations into these states in the conduction band, but experiment actually measuring current. So therefore, you need to go to mobility age in order to calculate these energies. And so if you define mobility age using IPR, so by, say, the threshold of the localized states, and calculate these excitation energies, so what you get are these excitation energies here, which are in good agreement with the energy range which is seen experimentally. So this is as far as we can go in trying to show that actually this type of states and this type of defects can exist in the system. So obviously using EPR would be very important, but because of the existence of these bipolaron states, it is very difficult. So still experimentalists are trying to do some EPR measurements, but as I have shown you before, for example, in the case of silicon dioxide, this requires irradiation at very low temperatures, and so that is experimentally quite challenging problem to do. So now, finally, there is hole trapping also in amorphous Hafnia. So you trap holes at auction sites in the system, which may be single or double auction sites, which form some bonds. And you can also form, so these states are shown here, so they have also a wide distribution of energies. And importantly, you can form also bipolarons. So these bipolarons have been also proposed in this paper here for, say, vanadium pentoxide and molybdenum anatase, etc. So we see similar bipolarons in Hafnia. So they are formed as a result of oxygen-oxygen interaction. And so the bond, oxygen-oxygen bond, goes down to about 1.5 angstrom, which corresponds to approximately oxygen 2 minus type of molecule. So clearly, this oxygen-oxygen interaction is facilitating trapping of these two holes in these oxides. So, because I need to finish soon, so I want to mention some of the things, some of the factors which affect this accuracy of this prediction, the special distributions of energies. So the first thing is that unlike what we have in crystal, say the initial states are partially localized. So therefore, the kinetic energy contribution to localization is varying dependent on, say, how strongly the state was localized in the first place. And so therefore, there is a big variation in trapping energies because, say, in order to say trapping energy is difference between how much you need to pay for localizing your wave packet and how much you gain from polarization. So in this case, you pay less because you already have localized the electron at precursor. So therefore, on one hand, trapping energies are bigger. On the other hand, they are very strongly distributed. So the amount of Hartree-Fock exchange is obviously an important factor, and I talked about that before. Different sample densities are another important feature in order to talk about distributions, because when we produce these amorphous films, or these amorphous samples, so they have all different densities, because they are produced using NPT ensembles, so they are allowed to expand, and then when we freeze them, they vary in size, and so therefore, this also affects distributions of these numbers I have been showing you, not the qualitative features. Finally, I don't have time to talk about this, but this is a very important factor here, reversibility of structural change due to trapping. So if you trap electrons or hole in these disordered systems, the structure changes irreversibly in some cases. So basically, the structure is metastable, so it is amorphous structure. So polaron is introducing a very big perturbation. So therefore, some atoms move into different positions. And then if you take an electron or hole away and reoptimize the structure, you get into a different structure. So this is what is called reversibility or irreversibility problem in this story, so one needs to be very careful about that. Now to finish, so we did, actually we studied several oxides. I mean, I talked about silica and hafnia, but we also looked at titanium, alumina, zinc oxide. So you can, here is a summary of what we find about amorphous phases with respect to crystalline. So for example, in silica, you don't have electron-hole localization in any form in quartz, but you do have in amorphous phase. In titanium, you have electrons, and you have also in amorphous phase, there is strong localization both of electrons and holes in much deeper states. In hafnia, I talked about. In alumina, it is much more difficult. And generally, the conclusion here is that, say, in all oxides, which where the top of the valence band is determined by p states, you always have hole localization, and in most cases by polarons. But if you have an oxide which S type of conduction band, there is no electron trapping. So say oxides like magnesium oxide, alumina, zinc oxide, they don't trap electrons in any form, but they do trap holes. And trapping energies are shown here. So for amorphous phase, due to existence of this disorder and precursor sites, trapping energies are much bigger. So these states are much more stable, and so they are responsible for real effects in devices, for example, for charging and things like that. And a conclusion, so what I was talking about on one hand was about functionals. So I think we need to have a discussion about functionals and which functionals are actually useful and how to deal with that. So it has been assumed for a while that, say, if you include a lot of exchange, so you can qualitatively at least achieve localization. So these results, which I have shown preliminary, but they show that actually the behavior of exchanges, so how much long-range and short-range exchange you include, is also maybe affecting what is going on. So it's much more subtle situation. I've shown that, say, electrons and holes trap in amorphous silica and hafnia in deep states, and so precursor sites are very important, and there are intrinsic features in these devices. I didn't have time to talk about defect creation, although the corollary of all of that is that actually when you trap these polarons, especially bipolarons, defects get created in these materials, and these defects lead to degradation of oxides. So to finish, I want to show, and thank the people who did most of the work. I mean, so Malud and Jack, so they worked a lot on hafnia. Tassem and David did most of the work on silicon dioxide, and Oli and John worked on alumina and hafnia sample. So thank you for your attention. Well, I mean, we cannot say much more than what functionals include in terms of correlation effects. So we do see that, say, in all of these oxides, which P and D character of bottom of the conduction band, you do have trapping. So this is may go back to Pecker and all these models, which we did long time ago, because the bands which we are having in these materials are narrow. And so therefore, the kinetic energy change due to electron trapping or the amount of energy you need to pay for, say, for localizing the wave packet is quite low, unlike in S-type of materials which have a very large dispersion. And so therefore, conduction band, say, or localizing electrons in those materials is much more difficult. This is my take on what's going on. I cannot say much about, much more than, say, these functionals give us in terms of real impact of correlation in these systems. I view it more in terms of, say, width of the bands and kinetic energy. I think that is an important factor. And so at this point, I also would like to make a point that actually we don't pay attention to kinetic energy in DFTs that much as we do pay to exchange and correlation. Although, say, basically it's all hidden in the functional, but multi-electron kinetic energy should be taken care of. And so there are papers now which talk about that, but this is an important part of this story.
Do you see a local moment at a half-moon when it comes to an electron?
Sure. Sure. Of course, it's the same as in titania or all this.
Now, lots of questions, but I want to ask a question myself. Take advantage of my role. Actually, I don't know, you say that in alpha quartz there is no localization in perfect crystalline. Actually, it localizes, and the reason is not correlation, is that when you excite the electron and the hole, the electron, there was an explanation in a paper of Steven Louis, and I think it was a good explanation, that the electron occupies the silicon oxide anti-bonding state. This breaks the bond. Essentially, it occurs with the breaking of the silicon-oxygen bond. You form two tandem bonds, and then here goes the electron, here goes the hole. So this is
was it exciton or was it simple?
an exciton.
Exciton, I mean, I published a paper in '81 which have shown this mechanism. I mean, so this was shown a long time ago.
Okay, but why then, but the electron could also occupy I don't know if a single electron, putting a single electron without any, the ground charge, I mean, without any compensating charge in silicon dioxide, such a low, the electric constant, I would feel a little bit uncomfortable.
Well, say, if you look at the, I mean, okay, so the whole story goes back for, 70 years, as we know. So there have been papers by Toizawa and other guys who looked at these stories. And so there's this phase diagram which shows you that there are situations when, say, holes are localized, but electrons are not localized, which corresponds to alkali halides. Then in quartz, we don't have both electron and hole localization, but we have self-trapped exciton. Forming because the electron-hole interaction is very strong, but both hole and the electron don't trap. If you take them separately, they don't localize in quartz, but they form an exciton. Well, I said already in my answer to Stefan, I think we need to look a little bit deeper into this equation because what we call this exchange correlation includes also kinetic energy contribution in it, somehow hidden, because what we have is independent particle kinetic energy in Kohn-Sham equation. But if we include, say, interacting electron kinetic energy, this is kind of all put into exchange correlation functions. So therefore, it is very difficult to disentangle all these effects with respect to polarons. Because if you look at the Pekar model, which we have a very nice introduction again this morning, so here is kinetic energy, here is polarization. So you need to squeeze the wave packet in order to localize the electron. You need to pay a lot of energy for doing that. So this kinetic energy should be represented correctly in these calculations. So we are not sure that actually this kinetic energy is represented correctly. Plus, we pay a lot of attention to exchange and correlation. So therefore, disentangle all of these things like, okay, so where is kinetic energy, where is exchange, where is correlation? The only my 5 Ps which I added to that is that one needs to pay attention also to short range and long range exchange. So this is the only thing which I can say. But I think semi-empirical theory cannot win. So it's you cannot say, okay, so this is kind of the best semi-empirical theory. It is semi-empirical theory. This density functional theory is semi-empirical theory. We are trying to fit some parameters, and I don't think we have a kind of golden solution for how to predict polarons yet. I think this would be my kind of opinion on that.